Welcome to the Metabolic Classroom. I'm Professor Ben Bikman, biomedical scientist and professor of cell biology. Thanks for joining me. In the lecture today, we are discussing the concept known as the Randle Cycle. Now, anytime you hear a name of something, it's named after the person who discovered it or discussed it most thoroughly, perhaps is the better word here. It's also known as the glucose fatty acid cycle. The reason I'm devoting time to talk about this in a metabolic classroom is because it's something that's been used, it's been invoked, I think somewhat inappropriately or incorrectly in certain social media channels. And so, but it's an interesting idea. It's one that I think has value in helping us understand metabolism a little better. And of course, hopefully there's some nugget in there that can influence habits to help you, all of us, make better decisions when it comes to nutrition. And again, ultimately, just getting a better understanding of how our body works and the metabolic function within it. Now, I'd already mentioned the alternative name, the glucose fatty acid cycle, named after Philip Randle, who first really identified this with his colleagues. This was decades ago in the mid-60s at Cambridge. And Dr. Randle and colleagues, when they published some of these papers, and I'll have a link to some really highlighting some of their seminal work in the show notes, what they wanted to do was understand fuel utilization in the heart. So it's important to note that that was the model for their experiments. And there may be limitations to this because heart is a unique tissue. There aren't a lot of tissues that operate metabolically like the heart does. Now, having said that, I don't mean to cast shade on the idea, on any of the ideas that we're going to discuss. I believe they have value, but we need to appreciate the model, which again was perfused hearts from rats. So a heart would be surgically removed from the rat, and it would be kept alive and beating. So nourished, properly nourished, and then infused through the blood system with nutrients, of course, glucose and fatty acids, and then analyzing the metabolism of these substrates or what's being used. Now, already I've mentioned a word a couple times that you need to understand, which is fatty acid. We all know what glucose is. Fatty acid is what is used for energy. However, that tissue is pulling it in, whether it's pulling it in as a direct free fatty acid, which always is coming from fat tissue, and that becomes an important point that we're going to highlight in this lecture, or whether it's a fatty acid that is pulled off of a triglyceride that is circulating on the blood as it is lumped into a triglyceride-rich lipoprotein like LDL cholesterol or VLDL. Anytime you get a blood test and it's giving you a triglycerides number, the triglycerides are just a part of LDL or VLDL. They're not free circulating molecules like free fatty acids are. So regardless, in the experimental model, they're infusing free fatty acids, which is something I've used in my own experiments. But in the body, just appreciate the fact that those fats that are getting metabolized could be coming from either free fatty acids, which are coming from the fat tissue, the fat cells breaking down their own fat, namely lipolysis, or it's coming from the actions of lipase, which is pulling off a fatty acid from a passing triglyceride molecule, which itself is in a lipoprotein like LDL or VLDL. Boy, well, that's a heck of a start, isn't it? I'm already getting pretty complicated. And that is, for better or worse, a bit of a theme of today's lecture. This is admittedly for a little bit, it's focused a little more for kind of biochem nerds. And I wouldn't have discussed this if I didn't think there was a growing general interest in the topic. It's very likely by now, if you've been swimming in the waters of even kind of social media, metabolic research or metabolic science, you've heard the term Randle Cycle. All right, now all of this has been sort of a history and a teeing up of the topic. At this point, you might not really even know what it is. In general, the concept is simply one to explain this substrate competition. In other words, how do we understand which fuel a cell is relying on? With the primary fuels at most cells being the cell choosing between using fats for fuel or glucose for fuel. Now, if we were being really, really thorough, we could include other fuels. There are more than just fats and glucose that provide energy to a cell. We could talk about ketones, and I will actually bring up ketones at the end if I follow my unscripted notes a little bit here. And even lactate, which is really a topic for another time. Lactate is a very viable fuel for many cells. So there are a lot of other energy sources that we could highlight. I'm focusing on the main ones, the ones that provide the vast majority of energy to a cell and most cells, namely fats and glucose. So again, the Randle cycle is this concept to explain this phenomenon of energy use at a cell, or bioenergetics, where you can't, the cell isn't going to use both. If the cell has access, if there's more fats available to the cell than glucose, no surprise, it shifts its metabolic function to rely on fats as a primary fuel source. If there's more glucose available than fats, no surprise, the cell will shift its metabolic processes to rely more heavily on the glucose as the primary fuel. Now, let's get into this in just a little more detail. That definition would be sufficient for just a lay understanding. You now know what the Randle cycle essentially is, or the glucose fatty acid cycle. It is this competition between substrate or energy sources at the level of a cell, this kind of battling between glucose and fats. Now, how does it happen? For those who don't want the kind of biochemistry mechanism, by all means, just sort of skip ahead for the next 5 minutes or so, or speed it up. But it is pretty brief, and I'm going to just touch it at a pretty high level. Now, this is a reciprocal inhibition. So if there's more fats, it's demanding its own burning, and it's generally shutting down the glucose burning. If there's more glucose, then it's demanding that it gets burned, and it's shutting down the fatty acid oxidation or the fat burning. So it can go both ways. And so without any particular order in mind, let's just discuss it first and foremost from the side of the fat getting burned. And why not start with that? Because that's the fuel that most of us would prefer to be burning for the sake of just maintaining body weight. After all, good luck controlling your body fat if you're not burning fat. Okay, so first and foremost, fatty acid oxidation inhibits glucose utilization. So when there's an increased number of free fatty acids in the bloodstream, it will increase the uptake. So the uptake of free fatty acids will be increased, no surprise, into the cell. And as the fatty acids are coming into the cell, the story's not over yet. It sort of gets activated, and it turns into a fatty acid. It gets bound to another molecule that kind of locks it in the cell, because the fat so readily comes in, the fat could readily go out. So once it comes in, there is some immediate biochemistry that locks the fat within the cell. And then it starts to commit to the pathway of what's called beta oxidation. Now, the term oxidation itself is really loaded and sometimes used inappropriately. When I'm referring to oxidation, I mean that the fat is getting burned for energy. Sometimes people refer to oxidation as a fat turning into a harmful molecule. To be a little more precise, that accurate, the word should be peroxidation when we refer to fats becoming these molecules of oxidative damage. That should technically be called peroxidation. Anyway, just as an aside. So when I'm saying oxidation for the purpose of this lecture, I'm talking about the molecule getting broken down for the sake of producing energy, or ATP. Now, again, back to the fat. If the fatty acid is getting burned, it's going through beta oxidation. As a result of this, it's producing two important molecules, acetyl-CoA and NADH. Both of these molecules, acetyl-CoA and NADH, will inhibit a very critical enzyme in glucose burning. So at the end of normal glycolysis, this is really deep stuff. So hopefully I'm discussing it in a way that you can understand. And if my goals are met, even share it with someone else. It's always my hopeful outcome. So at the end of glycolysis, at the end of glucose burning, right when the glucose wants to go into the mitochondria, it uses this complex enzyme called pyruvate dehydrogenase, PDH, pyruvate dehydrogenase. So normal glycolysis or glucose burning gets down to pyruvate. And then if the glucose burning is going to continue and go into the mitochondria, it has to go through this pyruvate dehydrogenase complex. Again, when you're burning a lot of fat, you're creating a lot of acetyl-CoA and a lot of NADH. And the NADH is particularly important for the electron transport chain or system, I call it, which we're not going to talk about. That's entirely too complicated and not overtly relevant to this lecture. Again, you're burning a lot of fat, you're producing a lot of acetyl-CoA and a lot of NADH, and those start to both together inhibit pyruvate dehydrogenase, PDH. When pyruvate dehydrogenase is inhibited, now glucose can't be fully kind of broken down. Even still, that's the last step of normal glycolysis before the glucose burning goes into the mitochondria. Also, when you have a lot of fat burning, you start to create a lot of what's called citrate, a molecule called citrate within the mitochondria. Citrate then can come out of the mitochondria and inhibit an enzyme further up on glycolysis, on that glucose burning pathway. So we now have 2 points of attack where when you're burning a lot of fat, you are inhibiting one of the steps towards the end of glycolysis, and then another step in the middle of glycolysis. So it's some of these products. So when you're burning a lot of fat, you're making various metabolites or metabolic byproducts. Then these byproducts, now, while being part of an essential part of fat burning and ultimately getting energy from fat, they also end up having this influence to tell the cell, hey, you're burning me right now, stop burning glucose. Now you know where that's happening. It's happening at PDH and the other enzyme that was a little further up, kind of at the midpoint of glycolysis. In fact, it's a critical regulating enzyme, which is it's a long name. It's PFK1. PFK1 gets inhibited as well. So that's how you could discuss it. If you want to sort of talk about this in various circles because you're really bored and you want to impress someone with your knowledge of metabolism, that's how you could discuss it. This part of it, at least. Remember, we've only covered one part of this kind of reciprocal inhibition, namely how fats inhibit glucose burning. And when you have a lot of acetyl-CoA and NADH and citrate, which you do, all three of those will start to accumulate as you are burning a lot of fat for some extended time. They will start to inhibit pretty quickly, actually, and despite what I said for some period of time. I mean, it's pretty quick. As those molecules start going up, they will inhibit the cell's ability to use glucose. Now, as I said, it's reciprocal, meaning this thing can go two ways. It's not just fats that are kind of beating down glucose with a club. Now, glucose can too. Sometimes glucose holds the club, and it's the one in charge. So now let's sort of flip this coin and talk about how glucose utilization can inhibit fatty acid oxidation. So when we have high levels of glucose, it will increase glycolysis and increase pyruvate. When we continue with this, increased glycolysis will end up resulting in the increase of another CoA molecule, this time not acetyl-CoA, but a molecule called malonyl-CoA. Now, there's still the CoA that they have in common, but they're different molecules. In fact, malonyl-CoA is made from acetyl-CoA. So when you continue to burn a lot of glucose, you start getting more and more malonyl-CoA. And then malonyl-CoA actually goes right to the mitochondria and shuts down the enzymes, an enzyme complex called CPT1, which is necessary for the mitochondria to pull fats in. So fats need to be burned in the mitochondria, whereas glucose have both an external mitochondrial burning and an internal mitochondrial burning. And PDH is the kind of intermediate, that pyruvate dehydrogenase complex that I mentioned earlier. That's how the glucose progresses from burning outside the mitochondria, then finishes all of its burning in. CPT1 is how the fats get burned at all. If you can't get a fat into the mitochondria, it's not burning. And so when you have a lot of glycolysis, you start producing a lot of malonyl-CoA, and then malonyl-CoA shuts down that entrance enzyme. So now the fats can't get into the mitochondria to be burned, and that's it. That's the one point really of regulation. So it's a little more simple than the reciprocal regulation that I outlined earlier, where with fatty acid oxidation, it's regulating glucose burning at a couple different points. Glucose burning is now inhibiting fat burning at only that one point. It's inhibiting CPT1, and it works because fats have that one singular kind of entrance. It's not as complicated. Nothing happens really until it can get into the mitochondria. Okay, now, as outlined in Randle's experiments, and the only thing people ever talk about is what I've just talked about. albeit perhaps with a little less detail, but the principle is still there and it's accurate the way I've heard it described in general social media circles. More fats results in less glucose burning. More glucose results in less fat burning. Even at that superficial level, it's helpful, it's important. Even then, you can start to see why I don't like the old adage of you are what you eat. I prefer this more accurate adage of you burn what you eat. If you're eating more glucose, no surprise you're burning more glucose. If you're eating more fat, in the absence of glucose, of course, then you're burning more fat. And the Randle cycle kind of makes some sense of that. However, it's not that simple. And even Randle himself and his colleagues never suggested it was that simple. So where people stop there, they have done a misservice, a disservice, not only to anyone who's listening to them, but even to Dr. Randle and his colleagues, because they went a little further and looked at the role of hormones. Now, before I get into that, imagine a situation where both substrates are high, both calorie sources are elevated. Imagine a situation where the person has both high glucose levels and high free fatty acids. How does the cell know what to do? Does it look at both and just sort of give up and say, I'm helpless? I can't choose between the two of you lovely substrates. I don't know who to give the rose to burn. How does it decide? What happens then if both are elevated? The answer is in endocrinology. There is a little known hormone that ends up telling the cell. If we look at the whole body level, and Dr. Randle included this in his work, we need to remember that if we go beyond the experimental model, which in this case was isolated perfused hearts, and look at the whole organism or the whole body, the cells aren't acting in isolation. How does one cell know what's going on with the rest of the body? How is a signal conveyed to it from the rest of the body? It's hormones that allow different parts of the body to talk with other parts of the body. Can you guess which hormone influences the use of the energy sources? Can you? Yes, you're right. Of course, if you're thinking that it's insulin because you know me too well, you're absolutely correct. Even the Randle cycle in the original experiments in the mid-60s looked at insulin and found that insulin had a tremendous role on dictating which energy source was used. It plays a critical role. It's not the only one, but it is extraordinarily important, and I would say it's the most important. So here are some of the key parts of that. And then we're going to look at some full physiological examples to really highlight the importance of this. So with insulin, we have the promotion of glucose utilization. Insulin does not want to burn fat, to put it in a bit of a silly way, as if insulin has some desire. Insulin, its actions coordinate to prevent the body from burning fat. It wants the body to use glucose as a fuel. It does so when it docks to its insulin receptor on a cell. All of its biochemistry at that cell is going to be, well, there's so much that happens. Insulin does so much. Much of it, the metabolically focused aspect of insulin, the nutrient focused aspect of insulin, is going to promote the use of glucose. Now, if it is tissues that need insulin for glucose uptake, it will ultimately open those glucose transporters called GLUT4. If a tissue has GLUT4, the glucose transporter number 4, then it needs insulin generally in order to act. That's tissues like muscle and fat. And that matters a lot because most of what we're made of is muscle and fat for the average individual. For almost everyone, it's muscle, except for the profoundly obese. And in that case, of course, it's fat. But even in the average individual now, it's still generally muscle and fat mass constitutes the majority of their mass. And they're insulin dependent for glucose. So they need insulin in order to open those glucose transport doors, the GLUT4 doors. So insulin does that directly. But even in tissues that don't have GLUT4, like the liver doesn't need insulin to tell it to take in glucose, but it still needs insulin to tell it what to do with the energy. Every single cell of the body will follow that pattern. Even if insulin isn't directly controlling the direct movement of the nutrient in, like glucose, it's still directly controlling what the cell does with the energy, including the Randle cycle. So not only is insulin stimulating the either direct uptake or the keeping of the glucose, and activating other enzymes further down, like PFK1 I'd mentioned earlier, hexokinase, which is the first step of glucose, locking it into the cell, whether it's going to get burned or turned into glycogen. Insulin activates that too. So it generally is promoting glucose, glycolysis. At the same time, it's inhibiting the breakdown of fat. Now, there's two parts here of fat to talk about: lipolysis, which is the breakdown of fat from the fat cells to be shared. And then there's the oxidation, or the burning of that fat. They're not the same. When people say fat burning, they sometimes only are actually referring to the breakdown of the fat, which is more technically to be called lipolysis. So there's two steps here. It's the lipolysis, or the releasing of the fat, and then there's the burning of the fat, which is the oxidation part. That's when burning should be used most appropriately. Insulin inhibits both of those. It inhibits lipolysis, and it directly inhibits fatty acid oxidation. So it doesn't want the fat to leave the fat cell. And even if there is some that's left the fat cell, it doesn't want the tissues like the muscle to burn the fat. So insulin is absolutely critical for understanding which fuel is going to be used. If insulin is high, it will both aggressively activate all of the glucose burning pathways and aggressively inhibit any of the fat breakdown and burning pathways. In contrast, if insulin is low, there is a much diminished signal to burn glucose, and there's nothing to stop fat breakdown and burning. So now fat breakdown and burning is just going nonstop. It's going unchecked. There's nothing really to inhibit lipolysis. Other people want to invoke other little hormones here and there, and others do have an influence, but nothing matters if insulin is low or not there at all. And we're going to get into that in just a moment. We're almost there. And so again, just to really put a fine point on it, if insulin is high, the body is burning glucose. And if insulin is low, the body is burning fat and glucose burning is shut off. This happens even if both are elevated. Insulin dictates which one is used. Now, with that point in mind, I wanted to be able to give you a real physiological example of this point. And diabetes is the perfect example, both type 1 diabetes and type 2. Of course, the difference with them, and there's far more different between type 1 and type 2 diabetes than there is similar. I will state this again, as I've stated it before. I think it's a tragedy that they're even put in the same family. The only thing they have in common is the high blood glucose. Everything else is profoundly different between them. They shouldn't be even lumped together. They're diseases of opposites. They're not diseases of similarities. With type 1 diabetes, there's too little insulin. With type 2 diabetes, there's too much. All right, now let's talk about type 1 diabetes first, because it provides the most extreme example here. And it's a perfect scenario where both glucose is high, the person is profoundly hyperglycemic, and guess what? Free fatty acids are also through the roof. They have extremely high levels of both substrates. So it's the perfect sort of case study here that I alluded to earlier. How do we reconcile this? And when there's no insulin, which one is the body using? So this diabetic body, again, tons of glucose, tons of fatty acids. The cell can't choose which one. And so who helps it decide? It's insulin. And if insulin is present, then the cell would know, okay, I'm burning glucose. If insulin is absent, as it is in this case, even though both are available, both substrates, glucose and fats, insulin, if it's absent, like it is in the untreated type 1 diabetic, it can't stop burning fats. It can't stop. It's just burning fats like gangbusters. In fact, it starts to burn fats so much that it can't. So if you take a tissue like the liver, where the liver doesn't need insulin for, say, glucose uptake, but again, it needs insulin to tell it what to do with the energy, it's burning so much fat that it starts to get to a threshold, if you will, and I'm describing this a bit imprecisely, but I think it's helpful nonetheless. Normally, a cell's only burning as much energy as it needs ATP, the main molecule of energy that is actually kind of energetic for the cell to use to get work done. Whatever the cell wants to do, it's ATP that allows the cell to do it. So normally the burning of energy is demand driven. The cell's saying, hey, I need this much ATP. And so the cell will say, okay, no problem. I'm going to burn this much fats or glucose to give you that much ATP. But if insulin is absent, firstly, the liver's primarily burning fat. but then it can't stop burning. There's nothing to really turn it off. And so even so the cell, again, this is a little imprecise. It's met all of its energetic needs where the liver is saying, hey, I'm full. I'm getting all the energy I need. So now the cell, which still can't stop burning fat, starts to turn it into ketones. So ketones are kind of this release valve where the liver cell is saying, one, I don't need any more energy, but two, I can't stop burning fats for energy. And so three, I'm going to start changing this energy into something else that other parts of the body can use, ketones, particularly the brain, of course, but every tissue, every cell with mitochondria will gladly use ketones for fuel. And of course, in the case of the diabetic, this is generally trying to make up for what is perceived to be a lack of glucose. Even though glucose is through the roof, in the absence of insulin, the cell can't really use it. It doesn't know what to do with it. So in the untreated type 1 diabetic, both glucose levels are high and fats are high. There's nothing to turn off the use of fats, so fats win. At the same time, there's nothing really to tell the cells to use the glucose because it's almost like the cells can't see it. It needs insulin to tell it what to do with that glucose. So the cell just sort of sees the glucose and says, yeah, sorry, I just don't know what to do with you. So don't come in. I'm not going to store you. You just keep circulating in the blood. Insulin hasn't come and told me what to do because there is no insulin. So it should be generally proof positive of the importance and indeed critical aspect of insulin when it comes to understanding the Randle cycle. If people are trying to discuss the Randle cycle in the absence of insulin, it doesn't work. There's no true understanding of the Randle cycle or this competition between substrates, fats and glucose. Okay, now there is also that I've been talking about it from the level of burning, but if we go one step back up, of course, there's what's happening at the fat cell, which is that in the absence of insulin, we can't stop breaking down fat. So that no surprise in the case of the diabetic, the person's losing an extraordinary amount of weight. And this is something I've alluded to before in various outlets, namely the phenomenon of diabulimia, which is when a type 1 diabetic, before they're diagnosed, they've become quite used to being able to eat whatever they want and be really, really skinny. Now they feel miserable. They're dying in this state where their ketones are getting into the realm of acidosis and their hyperglycemia is destroying blood vessels and nerves, but they get used to being thin. And now when they start taking their insulin injections, they aren't. They start gaining fat very, very quickly. They learn this, and unfortunately, in some instances, it leads to them abusing that fact and continuing to eat whatever they want and simply deliberately underdosing the insulin to stay thin. This is because if insulin is low, they can't stop burning fat. Thus, they're as thin as they want, albeit pathologically so, unfortunately. All right, now let's shift the topic then and look at what happens in type 2 diabetes. Interestingly, in type 2 diabetes, as I said before, that's when we have too much insulin. So this should be resulting in the cell shifting only over to glucose burning. And there is still some glucose burning, but because of the insulin resistance, it's created a unique, very odd scenario, which is a little more nuanced than it is in the case of type 1 diabetes, because there's more tissues involved in different ways. So insulin is high, but as the body has become insulin resistant, the fat cells are altered in their responsiveness to insulin. In fact, the fat cell, I argue, is one of the first, if not the first, tissue to become insulin resistant. Normally, insulin would be telling the fat cell to hold on to its fat. Insulin is saying to the fat cell, hey, I'm not going to let I'm not going to let the muscle use you for fuel, so just keep it in the fat cell. You just store that fat because I'm telling the muscle right now and the fat cell to use glucose for fuel. That can still happen to some degree. There is still some glucose utilization happening, especially because, remember, there are some tissues that don't really need the insulin for glucose uptake, and some degree of insulin functioning is sufficient to allow some glucose burning. But the high insulin is having this weird effect because, remember, insulin resistance is two things. It's both insulin not working well, like we have at the fat cell, where it's not inhibiting lipolysis anymore. So the fat cell is breaking down fat. So free fatty acids are higher. But the insulin may still be sufficiently working at the muscle to tell it not to use the fat. So once again, we come to this scenario where in the type 2 diabetic, we can have high glucose and high free fatty acids. In general, the type 2 diabetic is primarily using glucose and can't shift out of glucose burning. This is something I've alluded to before called metabolic inflexibility. Metabolic inflexibility is nothing more than the high insulin altering the Randle cycle, the glucose fatty acid cycle. In a healthy individual, you eat a mixed macronutrient meal with fats, carbohydrates, and proteins. Because there's an insulin increase, you go to glucose burning. Once you've gone through that glucose and insulin comes down, and you get into the fasted state, now you're fat burning. What had been noticed decades ago now is that in a type 2 diabetic or someone with insulin resistance, they're sort of stuck in that glucose burning mode, that even though they haven't eaten for some period of time, and in a healthy insulin sensitive person, they would have transitioned into the fat burning state of fasting. They don't. They stay stuck in glucose burning. And that's because of this high insulin that is reflective of insulin resistance. And of course, that's very much reflective of type 2 diabetes. So type 1 and type 2 diabetes both reflect the relevance of insulin in understanding the Randle cycle. Now, I debated on whether or not to share this, and I generally like these to be about 30 minutes. So I'll be very brief here because I think it's important, and it's something I'm going to touch on in a future lecture. So be sure to stay tuned for that, which is the relevance of insulin and the Randle cycle in altering hunger. This is particularly relevant in the type 2 diabetic. So I'm deliberately placing it here as we wrap up after talking about insulin resistance in the type 2 diabetic. The brain is unique. It doesn't quite fit into our understanding of the Randle cycle because it doesn't use fats for fuel. In general, even though it has access to fats, it's, I think, more correct to say that the brain uses fats for structure. It uses it to build stuff rather than using fats to burn for energy. So the brain's fuel choices are between glucose, which is a ubiquitous fuel source, and ketones. That's the brain's availability. And once again, the Randle cycle would be relevant here. A brain cell, like every cell of the body, just can't infinitely use all energy sources available to it. It doesn't need an infinite or an unlimited access to energy. It's going to choose one or the other. And I wanted to mention this in the context of hunger. Because if you have insulin resistance, the brain can become insulin resistant. That there are regions of the hypothalamus that can become insulin resistant, where particularly we have our hunger and satiety centers. As that part of the brain becomes insulin resistant, it can't pull in glucose as well. Even though there's plenty of glucose in the blood, the brain isn't getting it in very well because the glucose isn't working well, so the glucose doors aren't opening very well. GLUT4 isn't working particularly well. Now imagine in that same situation, because of the high insulin, reflective of their insulin resistance, what has happened to the ability of the liver to make ketones, which is a favored fuel by the brain, or of the brain. Of course, it's compromised. And so it's this particular metabolic tragedy where the brain, which has so much glucose surrounding it, isn't able to use it very well because of the insulin resistance. And the one fuel that it's crying out for, namely ketones, in the midst of this compromised glucose use, is a fuel that it doesn't have access to. It's not available, to be a little more precise, because of the high insulin inhibiting the liver's ability to burn fat. Because insulin is stopping the liver's fat burning, there is a compromised production of ketones, resulting in the brain going a little hungry. And if the brain is going hungry, not only can that contribute to chronic neurological pathologies like depression and migraines and Alzheimer's disease and Parkinson's, all of those have this aspect of glucose hypometabolism to it. In other words, a compromised ability to use glucose. But to compound the problem, we're not giving it access to the alternate fuel source, namely ketones. So I like to sort of jokingly invoke the rhyme of the ancient mariner here, which may sound a little familiar. The sailor who's on the sea, tossed and dying of dehydration, bemoans the fact that he's surrounded by water everywhere, nor any drop to drink. He can't drink it, even though he's surrounded by water. That's sort of analogous to the brain being surrounded by glucose, but it can't get it. And the one thing it's crying out for, the fresh water that we could provide this stranded sailor, would be the ketones in the case of the brain, to bring the analogy back full circle. So there's a relevance there, not only to the brain going hungry and contributing to pathologies, but if the brain is hungry, it thinks the body is hungry, and then it stimulates hunger. That's this idea of the fuel partitioning theory of obesity that I'm going to talk about in a future lecture. So stay tuned. And of course, insulin being extraordinarily relevant. Okay. As usual, I talk quite quickly as I'm generally freely thinking through these ideas. I hope that some of this sticks. Even though the biochemistry might have seemed a little daunting at first, listen to this again and slow it down, pause it, take a note, be true students with this lecture. It'll stick. But now I'm confident you know the most relevant information regarding the Randle cycle, the glucose fatty acid cycle, the reciprocal nature of the inhibition of these two caloric energy sources wanting to be used, each sort of demanding priority boarding onto this metabolic bus, if you will. But remember that there's a conductor. There's someone who's dictating ultimately which one gets to go on and be burned. And that is the humble hormone insulin. If insulin's up, the body is burning glucose or blood sugar. The body's sugar burning. If insulin's down, the body's burning fat. It's fat burning. One of those is ultimately better when it comes to maintaining insulin sensitivity and body fat. I hope all of this has been helpful. Thanks again, as always, for tuning in. Remember, until next time, more knowledge, better health.